Yeah, I think it's no. Okay. So, okay. So the concept of basis and dimension arises from the fact that if we are able to, okay, let's suppose if you are dealing with a lot of elements in the set, right? And if you want to, let's suppose, come up with a generic framework to address like how a particular function when applied on that set changes that set, and if we want to study that, then we want to be able to simplify that problem, right? We cannot just closely monitor each and every element in the set, okay, or make a record of, okay, this element in the set if applied on this function and transforms to this and so on and so forth. So we cannot just memorize all of those things. So basis and dimension essentially tries to identify what is the minimum uh, elements in the set that we can take and analyze, so that if we are like if we observe what happens to these elements on the set, then we'll be pretty much able to figure out what happens to every other element in the set. So let's say, for example, if I talk about numbers, right, then we know, right, prime factorization gives us a very easy way to express any number in form of prime numbers, right? Now the thing is, like, let's suppose tomorrow something happens so that every prime number is, let's suppose, if we are just squaring every prime number, right, let's suppose that's a function, then we do not need to explicitly like look into all of the numbers, right? We can just find a prime factorization of a number and then see like what is the power of each of the prime factors in that number, and then we can come up with what the value that particular number will take, right? So that's a very easy and convenient framework. So similarly, basis and dimensions operate on the same kind of a thing, wherein I talked about span of a set, right? So span was basically you take a bunch of elements in the set, you take their linear combinations, and whatever you can come up with would be essentially the span of the set. So basically, what the space it spans is basically all the linear combinations that you can, all the things that you can come up with a linear combination. For example, RGB ka linear combination would give you all of the colors in the space, right? So that's basically a span of RGB. Okay. So far, any confusion, any doubts in this analogy? No. Okay. So, hmm. So basis and okay. So basis is essentially defined as like you take these you identify few set of elements which are basically linearly independent. Now, I think I don't remember if I discussed linear independence, but yeah. So basically, they have to have two properties. These set of elements need to be linearly independent, and the combination of these elements need to span the entire vector space. Okay. So one of the very canonical basis that we're familiar with are x, y, z vectors, right? So let's suppose if we have these three vectors, right, 1 0 0 0 1 0 0 0 1, you can actually come up with any random vector, right? All you have to do is, let's suppose, if any random vector is like ABC, right? How you can form ABC is, right, A multiplied by this vector plus B multiplied by this vector plus C multiplied by this vector, and the sum of these things, like the linear combination of A multiplied by this, B multiplied by this, C multiplied by this, right? So this is basically one thing. So it has both the properties, right? It spans everything. Like basically, we can come up with any vector using the combination of these three, and corresponding A and B, C coefficients. And linear independence mean like basically you cannot just express one of the vectors in this set as a combination of other two. So I mean, here you can clearly see, right? That one is basically in the first dimension. So what, and you do not have one in any dimension, right? So any number multiplied by zero will essentially not be able to give you one, right? So that's why you cannot express any of the elements in this set as a combination of other two, right? If that was the case, right, then what we could have done is like we could have excluded that particular thing which could have been expressed in as a linear combination of other two, and then we can again come up with a basis, right? So basically, basis means like you just exclude all the redundant vectors and you include all those minimum set of vectors that are independent of each other, that basically you cannot create one of them with a combination of either of them, and combination of all of these will give you anything that you desire in the space. Okay. So and okay, so basis is something which is not unique. It's not like if you take a real space, let's suppose the basis has to be only these three elements. right? It can be like I can just write 3 0 0 1 0 0 3 0 0 1 0 0 5, right? That's also a basis, and that all of these vectors are independent. So basis is not unique, right? As you can see clearly. So that's why, I mean, one of the examples that they have written is this. I mean, and yeah. So yeah, so like I said, basis is not unique. And then like they have written a theorem here. It's basically like if U is spans, okay, they're talking about a bunch of elements U in a set, and they are saying that if that spans a particular vector space, then we can actually reduce it to the basis of set V. So essentially what this means is, let's suppose if I take all of these, let's suppose if I take 1 0 0 0 1 0 0 0 1 2 3 5 4 3 4 or something like that, then, and if I'm sure that all of these elements are will give me, the combination of those will give me anything in the set, then I can actually reduce that to linear like basis. I think we pretty much talked about this just earlier, that whatever element that you find that can be expressed as a combination of one of the other items, then you essentially like discard that, right? So if you keep on doing this iteratively, then you will end up with all the elements. Like you will not end up. So you'll end up with elements wherein uh, any of the elements would not, you cannot just express with combination of other of the elements, right, anymore. So just keep on discarding anything that you can create by combining any of the things, and then you will we end up, then you will end up with what you call a basis, like any basis, right? I mean, they have given a proof here, but I think it's pretty much intuitive. uh, okay, you can look into it, or I think if you is dependent, and yeah, essentially they're talking about the same thing, like you can just keep on removing the vectors. It's pretty much straightforward, I guess. Okay, so far any confusion, like what exactly basis is, span is, and why we are doing this stuff? Okay, everything's clear then. Okay, and then okay, there's another reverse thing that they have stated here is like, let's suppose if you start off with a set of linearly, like with basically a set of linearly independent vectors, and let V be a finite dimensional. I think it's finite dimensional vector space, and you can be extended to, yeah. You're saying something?
Yeah.
Yeah.
So basically, the example you gave, right?
Mm-hmm.
If you scroll above, basically some sort of I don't know what they are called, identity or what,
Mm-hmm.
I double zero, I zero 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 I zero. So
One,
basically,
one.
if we divide,
Mm-hmm.
basically I or one, we can say, or if you would say one. So basically,
Mm-hmm.
these can be an identity to all the all the vector spaces, right?
Sorry,
So
can you repeat the last statement?
so so basically, like the three vectors you have given over here, right?
Mm-hmm.
I zero 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 I zero 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 I, right?
Mm-hmm.
These can be identity to all the vectors spaces, like all like in every like all the vectors could be represented by these three.
Yeah,
So
combination of
any
these two.
reason to yeah, any reason to use specifically these? This is an example.
No, no, no. It's just an example. It's something which is we are pretty much used to, right? I mean, if you look at
Okay.
mm, mm. So essentially, like those vectors are this only, right?
Yeah.
This, and one thing will come out of the
Unit
one,
vectors.
right? So I mean,
Yeah.
so basically, if you see, right, the linear combinations of all of this will lie in the sphere. I mean, unit sphere, right?
Yeah.
So,
Mhm.
and if you are able to represent all of the vectors in unit sphere, then any of the vectors in the space is essentially a scaled version of
Span
everything.
of, yeah, yeah. So everything
So,
will come in the vector span, right?
so I mean, yeah. So this essentially, okay. This also brings us a very good point. Essentially, like if you are able to like find whatever happens in the unit sphere, then you essentially have the idea of whatever will happen in everywhere. Because everything else is just a scale, like a scaling factor. Like if
Yeah,
you
linear
know,
combination of that sphere.
hmm,
Uh, I don't know that would be a right term to call, but yeah, I got your point.
yeah. And similarly, you can take like I think you can take this also as a basis vector, right? Like, I mean, essentially this. I mean, all of these are 90 things, 90-degree things. What you do is it essentially rotate all like this particular thing just by a small angle phi, and all of those things will give you basis, right? It need not to be orthogonal. It needs to be orthogonal for linear independence. But if I'm talking about like if there's a just problem, okay, just give me the three random vectors that can express any random vector, like, any random vector in my space. I'll just give you, I can give you this, I can give you this, and I can actually give you this. These three will also combine everything. So I
Yeah,
can,
but those three will be like linear, like we could say
yeah, yeah.
all those three are orthogonal vector only, and we can say like the unit vector, right? That you gave, right? So
Hmm.
basically, essentially, they are the same with different angle of inclination of I, like
Yeah, what I'm trying to say
yeah.
is like for span, they need not to be orthogonal. I can represent
Okay,
any xyz random vector with this also, right? All you need is just a component in x and y and z. That's it, right? I mean, I
okay.
cannot represent any vector. Let's suppose if I have a vector like this and a vector like this,
Mm-hmm.
and yeah, and a vector like this, let's suppose, then I cannot represent any of the vector which lies out of this plane, right? So basically,
Yeah,
the vectors that I've taken is like this direction one, and then
it,
this direction one.
yeah. It's basically two vectors only. If we
Yeah.
have a like linear sum, right?
Mm-hmm.
I and J plane, right? Yeah.
Yeah.
Sorry if I am bothering you because like I
It's
do
okay.
ask
It's okay. It's okay.
some.
So the thing
Yeah.
is like, as long as I have a component from coming from either of the vectors in every direction, then that should be fine. But if I do not have any component in the direction, like even in single direction of a space, then I won't be able to reproduce anything. So that's the basic idea. That's it.
Okay, got it. Thank you, Bank.
Okay. Yeah. So this was clear, right? Basically, a set can be reduced to like essentially what that meant was like if I take the like let's suppose if I start off with a bunch of random vectors like this, like this, then I can take this set. I can take this set.
Hmm.
I can keep on discarding vectors which I can do. For example, this can become like we can create this using this and this only, right? Let's suppose if I talk about 2D space only, I forget 3D space. So I can create this also using these two, this also using these two, this also using these two. So I'll basically discard this and this. I'll be just left with these two because I know okay, this cannot reproduce this and this cannot reproduce this. So I'll just end up with a basis. So that's what the statement is.
Okay,
Okay.
thank you.
Is it clear to others as well? Like what we're talking about? The span, basis, and all of this stuff.
Yeah.
Okay, okay, ठीक है. Uh, okay, there is this one corollary which basically says that like if you pick any two bases, for example, let's suppose I picked up XYZ and then I pick up something which basically is a slightly phi rotated version of XYZ, or essentially are saying like if you come up with a basis of a particular vector space, then all of the bases have to have the same number of elements. Now this is a corollary, and this basically follows from the fact that we can take up the set and we can reduce it to a basis. So this is followed from here. So essentially, this means is that no matter what basis you come up with, the number of elements in that basis would be same. So for example, here we have the basis, right? So all of these bases, like so here you have three elements, here you have three elements, here you have three elements, and so on. So that's a corollary from this particular proposition that we can see. Um, okay. We can leave direction from now. Take this up later. Yeah, I can start with linear mappings. So okay, so essentially I talked about taking a number, right, and factoring it into prime factors, and then coming up with a way so that we want to analyze. Okay, in a new world, let's suppose if every prime factor has been squared, and I want to express my number all of my numbers again, then right. So I know, let's suppose if I picked up um, uh, suppose if I take 20, right? So 2 into 5 into 2, right? So if I know, let's suppose if I come up with a function which essentially says that, all of the prime factors in this world are squared. So I know 20 will be mapped to um, essentially what, 4 into 4 into basically 25. So that's basically 400, right?
Mhm.
Here it was slightly square because uh, consists of, I think it's just slightly square. Uh, it's not a very great example, but essentially what I'm trying to say is like you have this some value x and you want to map it to something, then it's sufficient to analyze the basis, right? Because like I said, right, if you know what happens in the unit sphere and if you know how that is going to be mapped to, let's suppose, another vector space. So let's suppose a unit sphere in another vector space is mapped to something like this, right? It's just scales, and this basically is like something. This is one in one vector space, and this is in another vector space. Then I know, right? I mean, since I can express any vector as is in the basis, right? So okay, let me just break it down. I think that will be clear. So I know, right? Any random vector x can be expressed as lambda b1. Let's suppose called b1 plus lambda 2 b2 and so on, right? So essentially, let's suppose if I apply some kind of function on this, right,
Mhm.
then I basically, that means this, right? And we know, since it's a linear map, so why linear map essentially has a property like function of x1 plus x2 is actually, sorry guys, I'm using trackpad, so I do not have mouse. Just so it's basically f of x1 plus f of x2. So we can break this down again and again. I mean, f of lambda x is basically lambda of f of x. So this can be broken down into lambda of f of b1 plus so on, right? Now, from here you can see, right? I mean, if I know how this transforms under a certain function, then I can construct any vector, like transformation of any random vector x, right? Is this clear, or am I just making it more messy by writing it this way? Okay, let me just ask someone. Dhruv, can you like try to explain like what the point that I'm trying to make here? Hello, Dhruv, are you there? Okay. Okay. Ritz, can you take a like a guess as to what I'm trying to explain? Okay, it's no one active. Am I audible? Hello.
Yeah, you are audible. I could
Okay.
try actually.
Okay, yeah, just go ahead and try. Okay.
So basically, you are saying about linear mapping. So in linear mapping, let's say if there is uh, a vector x that could be expressed as a combination of lambda a plus lambda 2b, right? So basically,
Mhm.
what we want to conclude is like if there's a function of x, then that value equates to a function of linear component of the vector. Basically,
Mhm.
a function of lambda x1 plus sorry lambda a plus lambda 2b.
Yeah, yeah. So essentially, what I'm trying to say is like if I know a certain thing is composed of certain components, right? And if I want to
Mhm,
find like what happens to that particular thing under a certain transformation, then what
mhm,
I'm trying to say is like if I know the transformation, what like how it happens on the components of what it is made
mhm,
of, then I essentially can actually just tell you like for any random element, you just give me like how you combine these components, and the
mhm.
transformation would be basically the combination of transformation of the components only. So essentially what I'm trying to say is sufficient to know like how you transform the basis of a vector space to uh, to express any transformation on any random vector. Okay, I
Got
think
it.
this is
It
this is
makes
pretty much intuitive, right? Like
Yeah,
let's
yeah.
suppose RGB say like I make any color and I know the RGB has to transform in certain way, then any color will also transform accordingly, right? If I know RGB पे क्या effect हो रहा है, right? So
Yeah,
that's
yeah.
that's the thing. Okay. Okay. So are like other guys active or not? I mean, I'm just hearing only one person is active. Like, can you just say hi or something? Like if you are active, anyone? Krishna is sad. Batata.
Yeah, I'm here.
Okay. Okay. So I guess Batata Group and Sat are not active. Maybe. Ritz, are you active? Hello.
Yeah, they are all active.
Okay. Okay. Are they messaging? Yes, mic not working. Okay. Dhruv, your mic is not working as well. Huh? Okay. 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 I just want to make sure like all of you are active because otherwise I'll have to repeat this again if next time people join. So okay. So far I think everything is clear, right? Now essentially they have what they are talking about is this only. So and when you talk about linear mappings, so what it means is like you take any two random vectors from your space, uh, and um, and you do a transformation. If that particular transformation has these two properties, then we can safely call that a linear map, basically a linear function. So what these properties are, like suppose you want to basically, let's suppose, classify a certain function as a linear mapping or not. What you do is just pick up any two random elements from your space and apply that function. You get some value. Apply that function on the first value, apply that function on the second value, and if both of those things are same, then we can say partially it's a linear map. Then what you do is for a second test is basically you take that particular random vector, a test vector, you scale it up, and then you find out the function value, and then I mean essentially this. That's it. Okay. Then if both of these two are satisfied, then you can safely say linear map. It's the linear mapping, and that gives you a very good power because the linear mapping, like entire matrix itself, is a linear transformation. So any tools that is available for matrix, you can use that. So any function, right, in random function, if it's a linear function, then you can use all the analysis as applicable to linear transformation for analyzing that function itself. Okay, this is a very strong statement that I'm making. So, and it's very elegant. Like you just have to verify these two things, and that's it. Like you can use entire linear algebra for any analysis that you want. Right. Okay. I mean, just to give you an example, if you have seen like image, right? Image rotation is basically a linear transformation. Like what that means is like the rotation transformation itself. The image is a matrix, right? It's just a bunch of numbers in a 2D, just pixel values in the 2D space, right? And if I want to rotate the matrix, then I just rotate the image. I just multiply that with the matrix. And rotation is because rotation is a linear transformation. And so that's one of the examples for linear transformation. And all of the, if you see like computer vision, especially like traditional computer vision uses a lot of matrix manipulation, essentially because uh, all of the operations, standard operation notation and then scaling and all of that stuff is linear. That's why matrix is like heavily used in computer vision problems. Like, you must have heard of homography. I don't know. Has anyone worked in computer vision here, by the way?
See, like for some small projects, yes.
Acha. Okay.
Uh-huh.
Okay. Not a problem. Yeah, I mean, essentially what I'm trying to say is, कि मतलब, since a lot of their transformation layers are linear, so that's why matrix is heavily used here. Now, an example of a transformation is like an integration and differentiation. So integration function essentially is a linear transformation. So uh, essentially, I think this basically means takes a and b value and maps to r. I think the r is basically I mean integration basically gives you area under the curve, right? So this notation basically means, right, a and b maps to an r, which is the real value. I think it's pretty much intuitive. Integration when we used to do like whenever a plus used to comes in between, right? We used to just break it up, and any scalar value can be taken out of the uh, of this integral sign, right? So that's essentially the property of. So basically, integration satisfies these properties, right? So that's why it's a same goes for differentiation as well. Like when you used to do differentiation, you can take coefficients out, and you can just separately differentiate each of the components separated by plus or minus, and then do that, right? And that will be equal to actual. I mean, so essentially, you see like these two properties are satisfied on these two functions, so that's why they are calling it linear. So this notation, just to give you this notation, this basically means like a function which is infinitely, like it can be differentiated infinite number of times. That's it. And this, when
Okay.
you see something separated by an arrow, it's basically what you do on the left side is you list the domain, or what you do on the right side is you list the. Okay, guys, after 10 minutes, like we just join on the second one. Okay? On the right side, what you do is just list the range of that function. So here, integration basically maps everything to a real number, right? As long as it's a definite integral. So that's why it's written in this way. Let's suppose if a function used to give if a function is supposed to give a vector, then that would be like here it would be like something like R2, R3, R4, where the number represents the dimension of that vector. Okay. Okay. So kernel. Oh shit, I forgot to study this. Kernel. Okay, I think so. Kernel is basically like if you take a linear. I think it's basically you take a vector if it is being mapped to 0 and it's part of the kernel, or I think it's this property of the transformation itself. So let's suppose if I take a linear transformation and if it maps like all of the vectors that are being mapped using that linear transformation to a 0 vector or an identity vector which we studied in groups, then all of those vectors are kernel for that particular transformation. Okay, we also call that as a null space because essentially, so something like this to give you a visual understanding. Let's suppose if we have a bunch of vectors here like this, and let's suppose we transform that using some function, and if all of them are being mapped to this 0, then all of these vectors will be called kernel of this particular map. Okay. So essentially,
Map to 0 in the sense.
but the vector is just being like if I apply a function on this vector, okay, then that is being mapped to 0 only.
सेंटर 0 मान लेना या फिर कैसे?
मतलब vector मतलब function of this vector is equal to a 0 vector. Okay. ये transformation T है. Let's suppose some कोई function, right? I can take some arbitrary function. For example, let's suppose I don't know. Maybe let's suppose if I transmit let's suppose for example 1 2 3 है, ठीक है? तो अगर कोई function अगर map कर रहा है इस पे 0 0 0 पे, it's very difficult to write actually. So 0 0 0 पे, ठीक है? ऐसे जितने भी vectors हैं जो 0 0 0 पे map हो रहे हैं under some function, then we'll call those as kernel of the kernel vectors of that function. As simple as this. It's just a definition.
ओके, इंट्यूटिव नहीं इसलिए मैं पूछ रहा था.
Can you tell me like इसमें क्या intuitive नहीं है?
Basically like किसी को 0 से मैप करना, right? So how can you map something to 0? Like what does it signifies?
मतलब like essentially, okay, let me. You know, जैसे I don't know, has someone seen 3 blue 1 brown का videos? So essentially there's like this there's an entire space, right? ठीक है? And when I said कि okay, does anyone know what is eigenvalue and eigenvectors, right? Eigenvalue and eigenvectors are basically all of that vectors जब उस पे ये transformation apply करते हैं. So basically transformation is essentially a matrix. Okay, you multiply that with a vector, and then you get a vector. Okay, let's suppose y. Okay. Now I was coming to this. The matrix is okay. What I'll do is I'll do one thing. I'll just talk about matrix and then I'll come back to this. Okay. So essentially वो transformation की हम यही बात कर रहे हैं अभी in context of vectors. Like there will be a bunch of vectors which will be mapped to a zero vector. Okay. So essentially what that means is ki like let's suppose if I have something like this. Okay. One something. Then I have, let's suppose, x, y, z, and it is being mapped to 0. Now, all of the vectors which are being mapped to 0 are called kernel. That's it. Okay, it's that simple. It's just a definition, it's just a term, nothing else.
Okay,
You know,
got
like
it.
under
So
a certain
basically,
transformation, a lot of vectors, I mean, there will be vectors which will be mapped to some random vectors as well, right? You are doing a transformation, right? So basically, let's suppose it apply a scaling transformation, right? So let's suppose this vector will be mapped to maybe this vector. Okay, let's suppose this vector.
okay,
The एक space से दूसरे space में जा रहा है. So ये vector will be mapped to this. If I multiply it with a matrix this, then there will be this. Let's suppose this vector which might be mapped to 0, and maybe this vector which might be mapped to maybe this. Okay, so all of the vectors which are being mapped to 0 is just called kernel. That's it for that particular
okay.
mapping. That's it.
समझ गया.
And null space भी उसको ही बोलते हैं. We call it a null space because the thing is कि the fact is like is a very I don't know if you can see it, but जो भी चीज को 0 पे हम ला दिए हैं उस चीज को हम वापस नहीं ला सकते हैं. ठीक है, बट जो चीज का मेरे पास एक यूनिक चीज एग्जिस्ट करता है उसको हम somehow वापस ला सकते हैं. ठीक है. Is this something?
रिवर्स ट्रांसफॉर्मेशन नहीं होता मतलब आप ये
हाँ,
बोल
मतलब
रहे हो.
अगर कोई चीज 0 हो गई है तो मतलब देयर आर लॉट ऑफ थिंग्स विच आर बीइंग मैप्ड टू 0, राइट? तो अगर तुमको बोला जाए कि मेरे पास 0 है, बताओ किस वेक्टर से आया था, तो हाउ कैन यू टेल? राइट? बिकॉज कर्नल स्पेस
Got
में
it.
अगर एक है तो ठीक है, आई कैन से ठीक है वो उसमें मैप होगा. बट जनरली कर्नल स्पेस में लॉट देयर विल बी लॉट ऑफ एलिमेंट्स, राइट? यू कैन नॉट जस्ट डेफिनेटली. सो दैट्स व्हाई दिस बिकम्स एन लाइक इसमें इन्वर्शन नहीं हो सकता है.
बेसिकली डिफाइंड सॉल्यूशन हो सकते हैं, डिफाइंड सॉल्यूशन नहीं होगा, ये बोल रहे हैं आप. सॉल्यूशन एग्जिस्ट ना करे ये गलत होगा, राइट?
इनफाइनाइट सॉल्यूशंस होंगे. ठीक है,
हाँ,
ये
इनफाइनाइट
जो
सॉल्यूशन.
उसका जो कॉन्सेप्ट है वो सब यहीं से आता है. ठीक है, एसेंशियली द लीनियर इक्वेशन इज दिस ओनली, राइट? ax इक्वल टू b. ठीक है, तो इनफाइनाइट सॉल्यूशंस तब होंगे जब मान लो when you are mapping this x to a b and इससे इधर जाने के कई रास्ते हैं. ठीक है, तो और तुम you do not have any other extra information that you can use to determine, so that's when that happens here. Okay, is this clear so far? Yes, so anyone else?
Not this last part. Zero versus everything. मतलब
What
zero
I'm-
से वापस नहीं आ सकते.
मतलब अगर जैसे हम तुमको एग्जांपल दे रहे हैं, ठीक है, let's suppose somehow I just write a function such that all of the people whose name start with M, I, and K will get let's suppose I don't know, get mapped to a particular something, right? And then I उस फंक्शन में हम जितने भी यूनिवर्स में सारे नेम है सबका हम एक मैपिंग रखे हुए हैं कि ठीक है, अगर किसी का नाम ध्रुव होगा तो उसका नाम भी ध्रुवी हो रहेगा, किसी का रिट्स रहेगा तो उसका नाम भी रिट्स रहेगा, राइट? बट एक्सेप्ट फॉर ऑल द पीपल्स हुज नेम स्टार्ट विद आई एम आई एंड लेट्स सपोज के. नाउ इफ आई लेट्स सपोज अदर जैसे अगर हम कोड डोमेन की बात करें, and if I ask you, okay, मेरा नाम मयंक है, let's suppose sorry, let's suppose MIK is being mapped to, let's suppose, a new name, like let's suppose I don't know, some agent X. Okay, now I asked you कि ठीक है, this is agent X, do you know कि कौन agent X था like originally? I don't know if I'm very clear with my example, but essentially there are 3 people who are being mapped to same name and then every other is being mapped directly. Now if I ask you who was agent X, then you will have, okay, ये भी था, right? You cannot just definitely say कि who was that. Okay, so my question was कि ये inverse आप नहीं जा सकते हो. एक अगर कोई भी value, it's not just about 0, I think if any value
It's about everything, right? Not especially zero.
yeah, not specifically to 0.
Another example would be, if I could think of, basically if we have a multiplication, like if suppose we multiply lambda, so in the equation lambda ax, right? So we don't, for different value of lambda, solution, the null space would be same, but as we don't know lambda, we cannot like pinpoint what was the actual a.
I mean, I'm not very clear on this, but I think sort of you're trying to say the same thing only. But it's a very general concept यार, मतलब अगर कोई चीज किसी चीज के बहुत सारे कैंडिडेट्स हैं और तुमको बस पूछा गया कि कौन है भाई उसमें से और कोई एक्स्ट्रा इन्फॉर्मेशन नहीं दी तो कैन नॉट से राइट. सो यू विल जस्ट से लाइक देयर एग्जिस्ट लॉट ऑफ सॉल्यूशन, दैट्स इट. ठीक है. स्पेसिफिकली अभी इस कॉन्टेक्स्ट में नल स्पेस बोलते हैं बिकॉज इट्स बीइंग मैप्ड टू नल, वी कैन जनरली कॉल जीरो नल वैल्यू. ठीक है. तो दैट्स व्हाई इट्स कॉल्ड जस्ट नल स्पेस. Then similarly you will have something like a column. You must have heard of column space, row space, and all of that stuff. And there's a relation between these things: null space, column space, row space. And then एक और कुछ होता है, चार चीज होती है. I forgot. I mean row. Okay, I'll just tell you. Row space is basically all of the vectors that you can come up with using row of the matrix. ठीक है. तो जैसे ये वेक्टर उठा लिया, ये वेक्टर उठा लिया, ये वेक्टर उठा लिया, इनको किसी भी तरह कंबाइन करो. Let's suppose 5 times this plus 3 times this plus 4 times this. So whatever you can come up, like basically row space is just a span of column vectors. Column space is just a span of column vectors. Similarly, row space is just a span of row vectors. ठीक है.